So today we have the pleasure to welcome Adrien Kuntz from CENTRA in Instituto Superior Técnico. And Adrien, we talk about non-linearities in black hole ring down. So please, you have the floor. Is it okay if people ask questions in the talk? So please feel free, and there will be also time at the end for questions.
So my talk is not so long, but you don't be a big issue for you. Time, and I'm very happy if I don't do the end of that. So thanks a lot for the invitation. I've been in Technico for a few months now. I arrived last November. And so this work has been working on it since years, approximately. A lot of the relevant experience there have been by different firms, Italy, CIA, United States, and also the Institute. And so, the topic that I want to introduce today is about, so I will talk only about GR, so the multiplication of gravity. I will also work on this, but only talking about GR. I want to talk about ring down, so the last part of the gravitation we've seen now when two black holes collide and produce a single black hole that has some oscillations. And I want to introduce you to the topic that we studied, which is non-linearities in these oscillations. So non-linear modes in ring down. And before to start with these non-linearities, I will just recap what is a ring down, what are these polynomial modes and linear modes, just to be sure that everyone is on the same footing. So, what are these polynomial modes? So we describe the system as a single black hole that has some oscillation. So I will describe it by a perturbation of a metric with respect to a Taylor angle that I will G bar here. That I call G bar here, plus a smaller fluctuation of other signal. Here I will, so in this talk I will just concentrate on the Schwarzschild background simplicity. So if you linearize your equation of motion around this background, you just obtain the Einstein so linearized at this metric perturbation is equal to 0. So now you want to obtain an equation of this perturbation that is as simple as possible. So you will use the symmetries of your background to simplify the form of this perturbation. So what do? You know that your background is time translation invariant. So you will decompose your perturbation in the Fourier basis with the frequency omega. You know also that there are background is rotationally invariant. So you will decompose the angular part in spherical harmonics, L and M. And so the coefficient that remains in front of all of this is a function that only depends on the radius, and this is the variable that we want to study. Here there is another thing that I want to mention, that so if you expand just a scalar function in spherical harmonics, so you know this kind of expansion, you do not have this level for a scalar function. Here the thing is that you expand around 2 times long. So in fact you will separate, you will split your space-time between an angular part and a time and radial part. And the angular part transforms under rotation. So in the end, we will have terms that behave as odd with respect to parity. So parity is the transformation that looks into the side of the sphere. So in the vectors and in the tensor, there can be terms that takes a minus sign when you go to the other side of the sphere. So these ones are odds, and the other ones are even. They go to the same when you apply a parity transformation. And of course, all of these components for different omega, L, and or different parities, since we stay at the linear level for the moment, they do not mix. So you have a separate equation of motion for each of these components. So I will also assume another symmetry that will be very useful when I go to nonlinear modes. And I will show afterwards how we can go beyond this symmetry, but for the moment I will assume that I have an equatorial symmetry in my initial condition giving this term. So what does it mean? It means that I assume that I have a plane of symmetry, and I will neglect that makes the plane of rotation of the black hole And so if I have this equatorial symmetry, you can work out that in fact the parity of a mode is completely given by L plus M. So for example, if L plus M is even, the mode here will be completely even. Okay, so once you've done all this, you can just plug this on factorization equation and obtain an equation of motion on your variable. And if you most of you know very well, this is a Ricci-Wheeler-Rosselli equation, which involves this tortoise coordinate that goes to infinity at the horizon and a certain potential. Here, the Ricci-Wheeler potential for odd modes in GR. And so what are quasi-normal modes? These are specific solutions to this equation with specific boundary conditions. A quasi-normal mode is a sort, you can think of it as a free mode of oscillation of a black hole. So at spatial infinity, you want to have a wave that is outgoing, which in my convention is minus I omega r, plus I omega r, sorry. And at the black hole horizon, you want to have a wave that is completely falling into the black hole, so minus I omega r. And if you impose these two boundary conditions, so you have a second order equation of motion, you know that the most generic solution is composed of a linear combination of two solutions. For example, if you impose one boundary condition, you kill one of these solutions. And if you want to impose a second one, well, it's possible only for certain frequencies. You have to tune your frequencies so that your solution to this equation respects the two boundary conditions. And so the frequency, in fact, so it's quantized, so it will depend on all these L, M, N numbers. So in fact, for Schwarzschild here, it doesn't depend on L, it depends only on L. And it will depend on the Leverton number N that just labels the different solution to this kind of boundary condition, because you have an infinite number of solutions to this quasi number. The lowest overtone, for example, for K equal to 2, has this value of the frequency, where here I take units where I set Gm equal to 1. And so, yeah, I've added a little label here to signal that this. This label is for the sign of the real part of omega. So if you impose this quasi-normal mode boundary condition, in fact, for each of these value elements, you still have two solutions. One which has the real part that is positive, and one that is the real part that is negative. So this just about the sign of the real. Something important to note here is that the amplitude of this quasi-normal mode, of course, this approach is completely arbitrary. It's related to the initial condition, just because you have a linear equation of motion. So the only way, a priori, if you want to develop an equal mass merger of black hole, the only way you can obtain this amplitude is to take a numerical relativity simulation and fit such a model, so such a quasi-normal model with arbitrary amplitude to this numerical relativity. You fit the amplitude and you obtain them, but you cannot predict them in perturbation theory, at least for one mass merger. And so this fit, it turns out to be very excellent. So here I show a plot from a recent paper showing this. So this is a numerical relativity simulation, and you fit it with such a waveform where, so your state here is decomposed with this quasi-normal mode with frequency that you impose to be the frequency that you just solve perturbation theory. So sometimes oscillating at this frequency. Something that I forgot to mention, but very important, is that because these frequencies are complex, and the imaginary part is always of the same sign, which means that your modes are damped. They are damped oscillations. So you put something oscillating at this frequency with the right damping time, proportional to the spatial harmonic that I was saying before, with an arbitrary amplitude. And the only assumption here is that this amplitude has to be a small number because you are in perturbation theory, right? So this should be small in this. And then you feed this amplitude to your signal. If you can see here that the fit is really excellent by eye, and the residuals are very smooth. Here, I think they fit it with 7 modes. Okay, so this is all the story for that I want to say for linear perturbation theory, and now I want to go into the nonlinear logic, so higher order effect in perturbation theory. And here, a priori conceptually, the story is very simple. You just go to next order in perturbation theory. So you just start the same thing, you write your metric as background plus a small perturbation of order epsilon plus a second order perturbation. And you want to obtain your equation of motion on this second order perturbation. So when you plug this in Einstein equation and you obtain your equation at order squared, you have a very nice structure because the operator that will apply to this second order perturbation will be exactly the same than the one that applies on first order perturbation. Very intuitive because you just linearize in this second order perturbation. So we have an equation of motion where on the left hand side you have a regular derivative operator here. But since your theory is nonlinear, when you plug this ansatz in Einstein equation, you have cross terms coming from order epsilon squared, so you couple linear perturbation with itself. And in the equation of motion, it makes a source term. So imagine you know this H1, then this H1 will source the second order perturbation. And of course, the expression of this source term is very heavy, but it's possible to obtain it just by turning the ground on Einstein's equation. So just by looking at the form of this quadratic source term, you can get an idea of how these second order modes will behave. Because if you let's take two polynomial modes and make the product of them. So here, this was my polynomial modes. You can see that for the time dependence, when you couple two frequencies together, the frequency that you take is just omega 1 plus omega 2. So this quadratic modes oscillate at the sum of linear frequencies. Because we have complex conjugates, also they can oscillate at the difference of omega 1 minus omega 2 star. The important thing to note here is that the real part of this can be added or subtracted, but the imaginary part always add. So it means they're always more damped than the linear mode of the same. Then you multiply two spherical harmonics, and this you know very well. You have to introduce the Gordon coefficient. So it means that the angular momentum of this second order perturbation is restricted by the usual selection rule. So the L is between L1 minus L2 and L1 plus L2, and the M number is given by M1 plus M2. You can also work out the parity of this quadratic mode, and because you have the same symmetry at the system, of course, the parity will also be given by -1 to the L plus M and before. And maybe the most important point of all of this is that the amplitude of this is simply proportional to the product of amplitude of the linear modes. And this is maybe one of the most important points of quadratic mode. I will discuss this in more detail after, but you can compute the amplitude that is proportional to the product of amplitude of linear modes. So before doing this, I just want to, the question that I want to ask now is, can we see this quadratic mode in numerical relativity situation? And the job that you can do is doing exactly the same thing as before, putting arbitrary amplitude in your model at fixed linear frequency, and trying to find an arbitrary amplitude at a fixed nonlinear frequency, which here I take to be 2 times the frequency of the fundamental mode to be here. I look at it on the 4/4 spherical harmonic and trying to fit this coefficient to numerical relativity. And what they obtained in this paper is exactly this quadratic scale that I was referring to before. So look at the upper panel here. This is the plot of this A44 as a function of A220, so the amplitude of the linear mode. And this, when you have different plots, the starting time of the shift is varied. And you can see you have really a quadratic relation between the amplitude of the quadratic mode here and the amplitude of the linear mode. This line is a quadratic relation. And the second panel is just to realize that if you plot instead the another linear mode, the linear for 0 versus the linear, then you don't have a quadratic relation. So yeah, things to really prove that you have second order effects in this mode that you can detect them in energy radiation. And now the question that I want to ask is, can we understand them better? And in fact, the thing that I want to show now is that you are not obliged to fit the coefficient to numerical relativity, like for the linear mode. You can compute it in perturbation theory, which in some sense is always better. Why? Because you don't have systematics when you fix your model. Because both when you do a fit, you never know how much mode you need to introduce. So this raises some questions, and you have much better precision, because in perturbation theory you can have lots of digits of accuracy. So yeah, this is what I want to say. I want to compute this quantity, that is the ratio of the quadratic mode amplitude divided by the 2 mode amplitude square. And so how can we do this? So remember that you had your second order equation of motion here. You do the same thing in that first order. You turn the crank, you plug in your metrics on stats, and at second order, you will find that a similar Rage-Wheeler-Zeerig equation on your second order variable psi 2, that I define very similarly to the first order case. And on the right hand side, you have a source term, which is huge. I mean, so we have this in the mathematical book, but it's several megabytes of density progression. So this thing is very ugly, but conceptually it is quite simple. And this is why I show you only a toy model, let's say, so what it should look like. So it looks like something that is proportional to a product of linear modes, with a function that depends on R in front. In fact, it can also, in the more generic case, but it depends also on derivatives applied. And so, a priori, now you want to solve this second order equation of motion. And you do this, by your favorite method of variation of constant or whatever. So you know that it is composed of a homogeneous solution and a particular solution. You can look, if you look at the homogeneous solution, so setting this source term equal to 0, you realize it is exactly the same equation as first order. What does it mean? It means that at second order, you renormalize sort of your linear mode amplitude. Because if you put quasi-normal mode boundary condition on the homogeneous equation, you get the same frequency, the linear quasi-normal mode. Okay? And this effect, I will not look at it. Why? Because I'm not interested in the linear mode amplitude. So since I don't know them, if I renormalize them, I'm not much interested. Here, something that I will much more focus on is a particular solution. The particular solution is different because it does not oscillate at the quasi-normal mode frequency, it oscillates at the frequency that is fixed by this source term, so the sum of two frequencies. And so it's important to note that if you sum two quasi-normal mode frequency, usually you don't fall back on quasi-normal mode frequency. So it's not part of the spectrum. And the thing to notice with this particular solution is that the amplitude, of course, is fixed by the source. This is why I say that we can compute the amplitude of this quadratic mode in perturbation. And a priori, the thing is conceptually simple. You just want to solve this equation with the same kind of boundary condition as first order. So you use the same method, people that know it. But there is just a little issue that I just want to say, it's a technicality, but still it's important to obtain the correct amplitude at infinity. So the issue is that if you, so let's imagine you want to impose quasi-normal mode boundary condition on this second order solution here, psi 2. Well, you will notice that if you plug this kind of ansatz in this equation here, and you look at large distance, you would have that the second derivative plus omega squared phi is something small. It will be equal to 1 over r squared infinity, which means that psi 2 is approximately away, but not just away. But the problem is that when you look at your source term doesn't behave like this. It just behave as something that oscillates, but is not suppressed at 1 over r. And so it seems you are in trouble because you are trying to impose boundary condition on an equation that doesn't want to admit this kind of boundary condition. So how can you do what does it mean? It just means, in fact, it just means that you chosen the wrong variable at second order. So these tangent variable, they were very nice at first order. But in fact, if you take the same definition that I skipped a bit under the curve, that this thing is defined in terms of atomic perturbation, if you take the same definition at second order, you obtain a quantity that doesn't really describe the amplitude, the correct amplitude at infinity. And so the way you can solve this issue technically is very simple. You just shift your variable. So you just redefine your variable. I want to define a new second order variable with time that is shifted with respect to the old one by a quantity that is quadratic in the linear mode with some arbitrary coefficients here, and I will fit this arbitrary coefficient so that I obtain the nice asymptotic S. Yeah. So yes.
Is there any physical or
Yes, I will say just after that. But it's a gauge transformation. Yeah. Why is this specific for it? So the fact that it's quadratic is just that because this second order mode is quadratic in linear mode. Then you put the coefficient in front of it. It does the most. I mean, the most generic kind of gauge transformation, which is quadratic into linear. So for the moment, I'm just talking of redefining your variable. So with this new variable, it's nice because you have a system that has a good asymptotics. At the infinity, it behaves correctly. At the horizon, it has to vanish also. And you can solve this equation for your new variable. Then the thing is that when you look at this cycle, you realize that this part here is exactly the gauge transformation that is needed to go from region wheeler to a gauge where you have affected to the gauge class. So transverse faceless, for example, for your method calculation. And so yeah, this exactly describes the gauge transformation that is necessary to go to a gauge where things are well behaved. So it's once you solve this this issue, you can really solve this equation by using the Euler method, for example, and obtain the quasi-normal number. So now I want to show this, which is maybe the most important part that I want to show here. So I show this ratio amplitude, second order mode amplitude divided by product of two linear mode amplitude that can be different at the other. Here on this axis, I put the first linear mode, so for example, the 2 to 0. I put this plus the time of the real part, so positive real part. And I combine it with another linear mode, which can be taken one of these signs here, with a plus sign for the real part, or one of these signs with a minus sign for the other. And I look at them in the minus part. So this corresponds to omega 1 plus omega 2, and this corresponds to omega 1 minus omega 2 star. And here I obtain the value of this ratio. Okay? So a priori, you can see from this that you have plenty of quadratic modes with amplitude that seems to be all below 1. I will come back on this at the end of the talk. But a priori, it's nice to have a ratio that is below 1 because it means that these effects are small in some sense. For example, let me highlight some of these points. So, for example, the quadratic mode that have been seen in numerical relativity, in fixed from numerical relativity, the one that I was showing before, is this one, this circle here. But the ratio is 0.54. And you would say, why is it this one and not that one that seems higher? But this thing is a ratio. So if you want to obtain the second order mode amplitude from the ratio, you have to multiply by the linear mode themselves, and these things can be small for some of them. Okay? So in the end, when you get back your waveform from this kind of ratio, it turns out the quadratic mode with the highest amplitude in most cases will be especially because I think the triangle is about yes. switch another two. And the value that we find is perfectly in agreement with the fit. So here it's a very nice demonstration that everything seems to work quite nicely in black-hole perturbation theory. I think this one here has been seen also in the N=5 in other numerical representation, and it's also another comment that I want to make here is that some of these modes are purely decaying. So, for example, if you take that one, it's 220 with a plus combined with a 220 with a minus. So it means you combine the same mode but with opposite real part of the frequency. So if you do this term, the real part of this thing will vanish. And it means it's a purely imaginary frequency. So it looks something a bit like a memory. No? It's not something that looks like a quantum mode. It does not oscillate. It's just something that purely decays, but it decays to zero. And it has a second key that you can compute with this. Okay, so any question up to that point on this quadratic mode? After that, I will go in more, let's say, more complicated stuff. But I think this one is the most important. So what I want to put on next.
Going to a question still that's relevant even in the linear analysis, which is so the quasi-normal modes, if I understood correctly, they don't form a basis.
Yeah, they don't form a complete basis.
They don't form a complete basis.
Yes.
So, what does that imply in terms of feeding a signal?
In terms of
feeding a signal.
So, yeah, sure. So the usual story is that quasi-normal mode, they tend to fit well the signal we say at intermediate times. Because if you look very close to the measure, you begin to have part of your signal that are modified by quasi-normal mode, and this is quite obvious because you go to the linear regime. So you have other contribution in the full response of, if you do, for example, if you study the gain function of irregular equation, you have several components, and the quasi-normal mode sum is only one of them. So you have a high frequency part, which is the thing that will contribute more to the measure. And you have also a part that is the tail, so something that does not decay exponentially like quasi-normal mode, but something that decays like a power law. And usually this tail is visible in the quasi-normal mode signal at late times. So usually you have something complicated close to the nerve, then the nice oscillation for quasi-normal mode. And then when the signal is very small, so it's not quasi-normal mode anymore, but it's something with a power law decay.
So is this
related? No, indeed, no, these ones are quasi-normal mode. They still decay exponentially. No, the tail is linear. Yeah, the tail is, you have also non-linear tails, but already at linear order you have a tail. And the tail is just when you, because you see that here, when I solve for quasi-normal mode, I solve this equation with particular boundary conditions. That is, of course, for a real measure, it's unphysical because you have the starting time, you have your black hole that collides at a certain time. So what you should do, if you want really to describe the collision of black hole perturbation theory, for example, a small black hole colliding into one, should develop this equation from a given time till infinity. And so compute the gain function of this equation. And if you do this, you will realize that you can decompose your gain function in several parts. One of them is the quasi-normal modes. One of them uses this solution that I computed here with this kind of boundary condition. And the other part is the tail and the high frequency part.
Okay. So my worry is about the uniqueness of the decomposition in quasi-normal mode.
Right.
So if they don't form a basis, I guess if you include nonlinear modes, the same mathematical state would apply. It's still not the basis, right?
Yeah, it's still the same.
So, I mean, when you try to do a fit, including nonlinear modes and linear modes, so what do we know about the uniqueness of that decomposition?
Yeah, well, the fit is a big problem in OSP because it is never clear how many modes you have to include into the fit. Sometimes if you include a lot of code, you can fit anything, no? And I'm very critical about this fix, but on the one hand, one of the I really want to work on some other way to make it completely.
Right. And could it be that there's some sort of degeneracy in fitting, say, we just linear quaternormal nodes including higher nodes versus including non-linear ones?
Yeah, so there can at least for nonlinear modes, the story is a bit more clear because so each of these modes has a specific frequency, right? So for example, if a frequency of a quadratic mode comes close by to another frequency of a linear spectrum, so then you can confuse these two because they lie the same. But in theory, if you have very good simulation with a lot of resolution, you can isolate your different frequency components, each one of them separately. And so a priori measure only the amplitude of the quadratic mode and measure only the amplitude of the linear mode. So what they're doing technically is to fit this amplitude, so to fit this model at different starting time. They will get some amplitudes and they check that this amplitude is independent of the starting time. And it proves that your signal somehow converge to a quadratic.
But that's in syntactic signals. So in realistic gravitational wave events, how close are we actually?
For the quadratic mode, you mean?
Yeah.
So the quadratic mode now, because now we can move to the fundamental mode. I mean, they already are not only, without so I don't think we can see the quadratic mode now, but so something that I will mention afterwards is that these are probably will be able to see them. You need a very good simulation ratio, but with these I could see quadratic mode. Then I will come back on.
Okay, but just to conclude, so your statement is that if we have a good accuracy signal, we could indeed distinguish the quadratic ones from the linear.
Yeah, because they are at separate frequencies. The sum of two coherent frequencies is not in the spectrum. But something that I would really want to do is compute the linear mode frequency, which you can do in experiment spiral. What I would compute is only which yeah, other questions? Yeah, let's begin. Let me continue on this. So yeah, here for example, I showed you your waveform where I include these nonlinear modes. So I took for example the parameter of this curvature given that we saw. I start from 10 m after the peak of the waveform. And so this continuous signal here is the sum of linear mode frequencies. So you see it's oscillating with a certain frequency, and it's also decaying exponentially. This is the log plot. And this signal here is a quadratic mode. So you can see very easily that they oscillate at 2 times the linear mode frequency. And also that they are surface quadratically, because when this one is 10 to the minus 1, this one is 10 to the minus 2. So here you can see most of the frequency of this quadratic mode. And when you add them to the waveform, this is at the division. So now I want to complicate a little matter. So I did this assumption of equatorial symmetry now, which is not always the case for blind matter. So I want to go beyond that assumption and consider auto merger where you could have split translation. In that case, what does it mean? It means that each LM component of your waveform will contain both even and odd components, not a single one as it was before. So you can define a sort of polarization parameter that is a mix of this polarization in each sector. So it's given by the amplitude of the plus amplitude, so the even amplitude plus I times the odd amplitude. So and you obtain a complex number that will describe how much you are far from the equatorial symmetry. Because For example, if one of these amplitudes varies, for example, you recover equatorial, let's say you have only a plus on amplitude here, then kappa is equal to 1 or minus 1. Okay? So the equatorial symmetry, this number is plus or minus 1. And what you can do is, in fact, not so much complicated for expressing the quadratic ratio, but it turns out that instead of one number, the ratio of quadratic linear amplitude that I showed before, you split inside your quadratic mode by 4 numbers. And what are these 4 numbers? It's how you can combine different varieties together in a quadratic mode variety. So, for example, you could combine an even mode with an even mode going to solid P. And the parity, the thing important to notice that here is that the parity of the quadratic mode is fixed by a symmetrical. So the only two you can vary in this ratio is the parities of the two linear. So you can combine even and even and odd and even. Yeah. And so the full ratio is just given by the sum of these 4 numbers times the polarization that I showed. Okay, so just to say that in the more generic case, it's a bit more complicated, but still, once you know the amplitude of the linear mode, you know the amplitude of the quadratic mode. The story is still. And for example, here it shows you how this ratio varies. This ratio of quadratic linear amplitude varies if you vary this polarization parameter. So it goes from 0.14 to 0.17, example here, so small variations. Okay, let me skip this. It's not so interesting. So the important question that also to ask is here I tell the charge indicate. But of course, we want to look at rotating black holes. So a priori, this ratio of amplitude also depends on the spin of the final black hole. And basically, you can do the same thing for perturbation theory, replacing the equation that I showed before with scale equations and the probability. So it doesn't change. Technically, it changes, of course, the way you approach the problem, but in principle, it's exactly the same thing. And you can obtain how this ratio of amplitude varies with respect to the spin. So this is the result from perturbation theory from paper here. And you see that the variation with, so this curve is the perturbation theory prediction, and these ones are the numerical relativity point. So you see it into equal to 12. And the variation with the spin is also small. It goes from 0.12 to 0.6. For the dominant quadratic. This other paper was based on fixed. So this one is the perturbation theory. Yeah, something that I find paper interesting because in the end they find that instead of 4 numbers, the quadratic modes depend on 3 numbers. And it's something that I did not understand completely quite well, but there seems to be a relation between these 4 numbers that I showed. Still to work out a bit more to understand where it's relation to. It's on this day, yeah. So now I want to finish with two things. The first is observability that I just mentioned before. So can you see this mode in the real data? And for example, here, so it's not easy to imagine that we can observe them because, for example, if you got the signal, so the strain amplitude of these modes. This one is the amplitude of the dominant linear mode, so the highest one. And this is the amplitude of several different modes. So some are linear, and one of them is quadratic. I think it's that one. Yeah, this one is the amplitude of the quadratic mode. So you see that it seems to be at the same level that, for example, the higher harmonics in the system. So a priori, with a good resolution, you could see this quadratic mode, and this is what we worked on paper with Sochiali and Liberty. Basically taking catalogs of events, realistic events for LISA or Einstein telescope and Explorer, computing the SNR of quasi-normal modes individually, and looking at the detection rate. For example, if your SNR in quadratic mode is more than 8, then you can detect quadratic mode. And here we put the number of events that it makes such a criterion for different astrophysical models. So the thing is that, of course, here the astrophysics varies a lot. Prediction of probability varies a lot for the number of events that you would see in this detector, because we know very little about the universe. So you could see that in some model you would have, for example, 10 detectable events with similar ratio supposed to be 8, but here you would have only a few of them, like 2 of them. And this one is for Einstein telescope and Cosmic Explorer. So a few events with relative mode and Einstein telescope and Cosmic Explorer. But for LIDAR, it seems that even in the most pessimistic models, you have a lot of events with nice interpolation with relative mode. For example, you see in some models you can have a ratio in the relative mode going to 100. Also. So a priori, yeah, it will be important to model them for LIDAR. This is the curve, yeah. So this study was done for the dominant quadratic mode, so the combination of 0 times 2 0. You could do this also for higher quadratic mode, and maybe you could see them with Einstein telescope or this other data that we're going to care the mode that I already mentioned. So this is still, I mean, this depends a lot on the astrophysical model, so this is still uncertain. And I think, in my opinion, the dominant quadratic mode is plausible to see them, the other one, maybe. And now I want to finish on the more theoretical notes on this. And I want to speak about stability of black hole. Because a priori, I said that it's nice that this ratio is small, because imagine that this ratio of quadratic modes to linear mode becomes big. What does it mean? It means that your second order modes blow up and becomes larger than the linear mode. So if your black hole is stable, in some sense, it shouldn't be alone, right? So it would signal the background of perturbation theory. So what we did was to look at what is the ratio in the economic regime. So for in the high frequency limit, so when the real part of the frequency is large, you know what are the quasi-normal frequency as analytically. And what I did is just run my code for computing this quadratic mode amplitude for higher and higher L. So for example, I take L times L, so I multiply 2 linear modes in the L harmonics, go in the 2L harmonic. And we obtain that plot, so don't look at that. So these points were from the paper that we think were false, and we because these points they give you that the quadratic ratio blows up. So it was clear that this should be wrong. This is why we decided to do this. And from the numerical result, it doesn't at all blow up, but it goes. So this ratio of L times L goes to 2L goes to things to go to some constant value, which is close to 0.2. So we were very happy with that thing, but then we decided to look at other combination of linear modes, also in the economic region, because you can combine a lot of modes together. So we decided then to look at the combination of L times 2 going to L plus 2. Yeah? A linear mode of L going to the linear mode 2 going to L plus 2. And here we were a little bit surprised because it seems that the ratio goes up. So what does it mean? Like, so this was our result. This one was the result from the other paper. It is not in agreement with ours. But our result seems that, so we checked this, and it's a linear scaling of the quadratic ratio with L. So it's proportional to a constant times L. So what? Yeah.
Sorry, but since the ratio is exactly what you said before that.
Yeah, exactly. This is what I want to say now. It's a ratio. We shouldn't never forget that it's a ratio. And the thing is that, so let's imagine that this ratio scales like L. If I had a perturbation with a constant linear amplitude of order epsilon, it's small, I could have a perturbation of quadratic mode that becomes larger than the linear mode amplitude because this ratio here is just L times epsilon. This is R times the linear mode amplitude. So if I could find a perturbation to excite me with a constant linear mode amplitude, I could blow up my black hole. But of course, in reality, it's never possible to find polynomial mode with constant amplitude if you go to higher harmonics. It will always decay. And you can see very easily that it's the case just, for example, by computing the flux of energy from a perturbation from, for example, a particle that you make orbit around this black hole. So the flux of energy is basically given by the frequency squared times the amplitude squared. And if you want this term, of course, has to be convergent. If you have a finite energy going out of the system, it means that this has to scale at least at L to the minus D. So it decays, and it decays in such a way that L, so the L times epsilon, which epsilon is L minus real, is still going to 0. But notice that if we have found something that was going at L squared, you could blow up in some situation your black hole, which we've done here. So it's still in the reflection. Of course, it's, we have also the result from more mathematics studies that charge nonlinear stable. So we have to find this. Okay, so I will just conclude and say that we should try to include this quadratic mode in our Wendell waveform. If you want to have this ratio of amplitude, it's all available at this address here. And so this amplitude of quadratic mode is completely determined by the amplitude of the linear polynomial mode and the mass of the spin of the Feynman level. So if you want to include it in a waveform model, it's nice now because you don't need, for example, if you want to fit an numerical relativity waveform, you don't need additional parameter, fitting parameter. You can just include these modes, which will somehow enhance your fit without any free parameter for the dynamic. Okay, that's what I was thinking.
Alexander, you have a question?
Yes. So, this study of the stability of the black hole expansion is like a proof of concept for methods. There are similar
Proof of concept for my method would mean that the code works, for example.
Yeah, that the mathematical say
Yeah, right.
it's correct, or
Yeah.
there are situations in which I should expect certain instability.
So for Schwarzschild, we expect it to be stable because there is it's a field that I don't know too much, but there are papers on nonlinear stability of black holes. And so it's proved, as far as I understand, it's proved for Schwarzschild that Schwarzschild should be non-linearly stable to perturbation. It's not yet true for Kerr. So here, since I did this for Schwarzschild, we were expecting to find that the black hole was stable because the way that we it's mathematical. The Kerr case, I think everyone expects that it will be non-linearly stable also. So I will be interested in evaluating that stuff just to confirm that Kerr is stable to second order.
What would be the implication of, let's say,
I don't know. I don't know, but I don't expect to find. Yeah, exactly. But exactly, there are no wrong. Yeah. What does it mean if you black hole becomes unstable to perturbation? Yeah. I don't expect to find something happening this time. But still, it's nice to see that your black hole is stable to second order.
It's not some methodology like singularities.
Yeah, something like that. Yeah.
So I was wondering, maybe you haven't looked at this, but people calculate vibrational modes of stars, as you know.
Yeah, right.
So, for instance, the sun, it's the cosmology.
Yeah, right. So here
do they see quadratic modes?
But here is a quadratic mode induced by pure gravity. So I guess if you
But my question is, they measure these modes for the sun and actually other stats, but for the sun, because it's supposed with high accuracy, which gives a lot of information about the internal structure of the sun.
But yeah, so.
And my question is, and I don't know, and I'm asking you in case you know, do they measure only the linear spectrum, or they can go and measure, is there any evidence for, you know, non-linear modes? Because there are harmonics as well.
So I don't know too much of visual stuff, but I think that these oscillations are due by special resistance or in your equation, matter oscillating, so it's not gravity oscillating.
No, it's not quasi-gravitational, quasi-normal. My question is, if they measure the non-linear modes in the star oscillations.
The question is non-linear in what? Exactly. Because if you see your metric inside a star is still very.
No, it's just fluid. I mean, it's just fluid. So the fluid.
The non-linear.
Yeah, like in anything in which you have non-linear equations, because these fluids will obey non-linear equations.
Yeah, sure. Okay.
Then my question is just out of curiosity,
no.
can these people measure non-linear modes, or is it only linear modes?
I don't know. It's interesting, but I don't know.
It's not anything, but it's
no, priori,
it's yeah, for others start is harder, but it's a kind of a private field because it's related then to variations of the luminosity. But for the sun, because it's much closer, you measure this oscillation, huge accuracy, obviously. So this is a field that has been thriving for many decades.
That's an interesting question. I don't know.
You were talking about, and I thought about it because I've heard several talks about cosmology, but they always discuss, you know, a linear spectrum of oscillation. So I was wondering.
Yeah, I have no clue if you have some old visual there.
Or people might consider that, probably they have.
Yeah. Well, I don't know, but I will touch it.
Are there more questions? Is there a question on Zoom?
No.
Oh, that's something else. Well, I just discussed. Do we have time, or we can?
We have a few minutes.
Right. Well, and of course, something else that has been undergoing a lot of discussion is this question about spectral instability that you know very well, right? So I guess the conclusion is that, say, the linear mode, even if there's the first fundamental mode, even if there is some sort of small perturbation, and your first non-linear mode is actually essentially the square of the fundamental mode.
Yes.
But I guess that would apply.
Yeah, I think also the next thing with spectral stable will be the same way. Yeah, I think exactly the same way, because also the wave function. I mean, one problem with spectral instability is that the wave function blows up at infinity. You know, the wave function of QNM. If you go to see, yes, here. So you see that time. Yes, here. So you see that if you have something that is down exponentially in time, it implies that it blows up with the radius. So the wave function of quadratic mode of the polynomial mode, sorry, is something that is large. And all of the spectral instability is due to the fact that at large distance you seem to have a blow up of the spectrum. Because of course, if you look at the signal in the time domain, it doesn't matter at all, because the blow up is sort of cut off by causality condition. So you cannot go to very large distance of your black hole, interact with that thing, and back react on your quasi-numerical spectrum in a time that is too short.
But in frequency domain, that's what you see.
Exactly, the frequency domain.
Actually, this graph, is it what you were mentioning that at date times it's you have the tail?
Yeah, can we see? Yeah, probably yes. Here you have the tail, but I'm not sure, but it could be. The tail that starts to filter and the filter is less good because of the.
Another question? So maybe you can stop it here. Thank you again.
Thank you.